efficacy leads to complex malaria patterns. So to sum it up, insight into the sensitivity of malaria dynamics on temperature are useful in assessing the potential impact of changes in temperature on malaria risk. Also, a malaria control program which ensures that ITNs are replaced regularly and early enough, and that educate at populations at risk on proper use and care for ITNs is necessary for reducing the burden of malaria. So just to have a quick introduction. So we know that malaria is one of the deadliest and most common diseases of humans that is spread by mosquitoes. It affects humans in many parts of the world, especially humans in tropical and subtropical
I don't know how to
regions.
put these things in word.
And apart from that, about 95% of the global malaria cases in 2020 were from Africa.
How to write it?
And
I don't know.
also, ITNs have been instrumental in curtailing or controlling the transmission of malaria significantly. Nevertheless, the success of this intervention is challenged by many factors, and they include mosquito resistance to insecticide use in ITN, the waning of ITN efficacy, and also improper usage. Malaria control is also challenged by several environmental factors that include temperature, reason being that the parasite and also the mosquito themselves, they are sensitive to temperature. So in particular, temperature is necessary for the growth and survival of the malaria vector and parasite. So it is therefore very important to acquire insight into the significance of temperature and the decay of in ITN efficacy over time, and how this interact with the transmission dynamics of malaria is very, very critical for the implementation of more effective control measures. Therefore, in this study, the decay of ITN efficacy and seasonal changes in temperature are incorporated in a model for malaria, and the model is used to assess the role of variation in temperature, decay in ITN efficacy, and control-related parameters on malaria prevalence. So here we have the aim of the study, the questions, and also the objective. The aim of the study is to assess the impact of interaction between temperature and waning ITN efficacy on the risk of malaria transmission and the success of ITN programs. And the study answered the following question. One, what are the effects of decaying ITN on malaria transmission dynamics? What are the effects of the replacement time of ITN on malaria transmission dynamics? And also, what are the effects of the interaction between temperature and decaying ITN on malaria transmission dynamics? And the objectives that correspond to the questions follow after. So straight up to the model. So the model study here was constructed by dividing the total human population into 4 subpopulations, and those are the susceptible, the exposed or incubating individuals, the infectious, and also the recovered. And the population of the mosquito is subdivided into 3 subpopulations, which are the susceptible, exposed, and also the infectious mosquito. And here we have the schematic diagram illustrating the transmission dynamics at the human and also the vector level. The broken line here represents the interaction, and then the thick line represents the transmission. The transition from one compartment to the other. So, and here we have the assumption. It is assumed that all birds in both the human and the mosquito population are into the susceptible classes. There's no vertical transition. So following the schematic diagram in the figure just shown, and the tables, and the model parameters in table 1, which we will soon see, we have this model equation. Looking at this model equation, the initial conditions were not stated, even in the paper also, and that's a kind of maybe omission by the author. And we have also seen this also in some papers, that the model we presented and the initial conditions will not be included. So this is not correct, in that this is not presented to us an initial condition problem, and that should be checked by other authors also. So here the theta is temperature in degrees Celsius. So the dynamics of the total human and mosquito population are given by equation 2. That can just be obtained by summing the change in the human population and the change in the vector population. They were going to have this. So as in Ngogula et al., the mosquito birth rate is modeled through the logistic growth functional form, which is given in equation 3. So we have the alpha v theta equals to all of this, and this alpha v theta is defined as what we have here. The alpha v theta is just talking about the birth rate of the adult mosquitoes, and then the meaning of each of these symbolic representations are defined below, where the the Xi is number of eggs per female mosquito per day. The PE represents the survival probability from egg to adult mosquito. The phi E is development rate from egg to adult mosquito stage. And then 1/that gives us the duration for development time. Then we have the KV, which is the mosquito carrying capacity, and that is due to the fact that there are limited resources available for mosquito sustenance. So what follows are the definition of the causes of infection that are given in the equation here. So here we have the definition, and followed by with that we have the table for the parameters. So we have the parameter, their description, their unit. So the unit of the parameters here are given per day. So we have the baseline value and also the range of each of the parameters. So then we have where beta T theta is equals to is the mosquito biting rate, and this mosquito biting rate is regulated by the coverage of heighting hen, and here we have the efficacy of the heighting hen. So the efficacy of the heighting hen is defined in equation 5 and also in equation 6. And the efficacy of the heighting hen considered here are one, the protective efficacy and also the killing efficacy. The protective efficacy on the human part, then the killing efficacy on the mosquito part, and respectively they are given as equation 5 and equation 6. The T here, just like I have said earlier, the B naught is the community ITN coverage, which ranges from 0 to 1. That's just like from 0% to 100%. And then we have the E naught, which is the initial protective and killing efficacy of ITNs, and T is the effective useful lifespan of ITN. These functions are defined in such a way as to capture the dynamics of the net in terms of the efficacy in protecting humans from the mosquito bite, and at the same time killing the mosquito in order to reduce their population. Why am I having this question mark? So the heightened efficacy for protecting human from mosquito bites is given by the equation 5 and 6. Sorry, these are just error. I don't know why it is like this. And for killing mosquitoes that land on ITNs, given by, as I've said earlier, equation 6, designed to account for the fact that once insecticide in the net is lost, the initial efficacy of the ITN is reduced by approximately half. So those are what these actually account for. These functions that are defined here, they account for the dynamics of the net. Just like it was stated, when, for instance, now for the killing effectiveness, when T, this small t, which is the time, is equals to T, which is the effective useful life of the heighting hen, then this is the efficacy is reduced to half. All right. So also, since ITN become less effective over the course of their lives, because their efficacy decline with time as a result of several factors that include misuse and physical wear, the ITN efficacy functions 5 and 6. Sorry. 5 and 6 are decreasing functions of time. Furthermore, the functions account for the fact that ITNs are replaced following the expiration of their effective useful lives. It should be noted that other functions also can be used to capture this efficacy. Other functions like the modified ill or Weibull functions can also be used. So some of the mosquito-related parameters of the model 1, for example, the egg to adult, the mosquito biting rates, the mosquito extrinsic incubation period, the number of eggs, all of these depend on temperature and other environmental and climatic conditions. So there are two functions that are used to model this dependency of these parameters related to the mosquito. There are two functions used to represent their relationship, and those are the Berry function, which is what we have here, C theta equals to theta minus theta mean, where theta here is the temperature, and then the theta mean here represents the critical minimum temperature. The theta max here represents the critical maximum temperature. Then we have the other one, which is the quadratic functional form, which is Q theta squared plus R theta plus S, where K, R, and S are phase parameters, and they are being used in in several words. So the parameter values associated with temperature-dependent functional forms are presented in the table that we can see here. So the first one here represents the Berry function, while the second one here represents the quadratic function. So what we are seeing here are the coefficients based on each of the functions. These are the coefficients. These are the values associated with the Berry function, while this one are the values associated with the quadratic function. So, and the unit of these parameters are just per day, except for probability of survival from egg to adult stage, which has no unit because it's survival probability, it has no unit. So on the other hand, we have the function, we have this function to cater for the value of theta, where theta m and theta a represent the average yearly temperature and the amplitude of the yearly temperature fluctuations, respectively. Is used to incorporate seasonal variations into the model malaria of equation 1 as presented above. So here we want to look at analytical results for the special case in which ITN efficacy is constant and temperature is not considered. So now we have analytical results obtained when the ITN efficacy is constant and temperature also is not considered. That is, those parameters that are temperature dependent, they are kept constant, and the ITN efficacy, which declines over time, which is a function of time, they are also kept constant. So we have a constant. So equation, so the equation 1 can have 3 possible types of equilibrium points. That is our model equation, and those are: 1, the mosquito-free equilibrium, which depicts a situation in which there are no mosquitoes in the community; a disease-free equilibrium, which represents a situation in which there is no malaria in the population; and an endemic equilibrium, which represents a situation in which the disease is always present at a certain level in the population. So this equilibrium can be obtained by just setting the epsilon beta, epsilon d, and all of to be constant in equation 1, setting the left-hand side of the modified model to 0, and solving the system of algebraic equations of the variable. And those were the things that were done here. So the model equation with constant ITN efficacy. So we have the mosquito-free equilibrium, we have the disease-free, equilibrium obtained as this, where Rm is equal to alpha V over UV. So it should be mentioned that the disease-free equilibrium exists when Rm is greater than 1. When Rm is greater than 1. Let us not forget that the Rm is just like the reproduction number for the mosquito. So it has to be more than 1 before we can have the disease-free equilibrium, which represents a case where there's no malaria in the population, although there might be mosquitoes in the population, but it represents the state where there are no malaria in the population. When Rm is less than or equals to 1, only the mosquito-free equilibrium therefore exists. So the threshold quantity Rm is called the vectorial reproduction number. It is defined as the average number of new mosquito produced by a single female mosquito in an area where there are no mosquitoes throughout the lifespan of the mosquito. So using the next generation matrix approach, the disease-free equilibrium are used to compute the reproduction number, that is the spectral radius of the matrix this of the model 1. And here are just the computation of FV inverse, and the reproduction number is given as what is represented in equation 8, as what is given in equation 8, and some A0, A1 up to A4, they have their representations in this place. So now, because ITN is integrated into this model, so the reproduction number being computed here is the control reproduction number, which is also called the effective reproduction number. So it's a threshold quantity that can be used to determine whether a disease can be contained, that is when R is less than 1, or establish itself when R is greater than 1. And it's just talking about the number of malaria cases that an individual can cause during its infectious period in a population where some are already making use of ITNs. So it should be mentioned that RC becomes the basic reproduction number when no malaria strategies are utilized. But here we have ITN, that's why it is called the control reproduction the control reproduction number. So the reproduction number, RM and RC, will now be used to establish the stability of the mosquito-free and disease-free equilibria. So the Jacobian of the system at the mosquito-free equilibrium is given by this. So we have that the set of eigenvalues for the Jacobian are what is given in this particular set. So all the eigenvalues are real and negative if Rm is less than 1, and that can actually be seen in this place. That if Rm is less than 1, then this one will be negative. Let us not forget that we have defined the values of A1, A2, A3 above. So we have, hence, the mosquito-free equilibrium is locally asymptotically stable if the vectorial reproduction number is smaller than 1 and unstable if it is bigger than 1. That is for the mosquito-free equilibrium. Furthermore, it can be shown that the mosquito-free equilibrium is globally asymptotically stable if Rm is less than or equals to 1. So this is done by using the Lyapunov function, which is defined as this, and we can see that clearly it is greater than 0 for all NV, which is the total population of the mosquito, not equal to 0. And we know that this Lyapunov function is only equal to 0 only when NV is equal to 0, and this satisfies the condition of the Lascelles invariance principle. And also, on the other hand, we have that the derivative of the Lyapunov function is less than 0, and that's why we have here that by Lascelles invariance principle, the mosquito-free equilibrium solution is globally asymptotically stable whenever Rm is less than or equals to 1. As we can see in this case, when Rm is less than or equals to 1, then this will be positive, and because this is positive, this will always be less than 0. Now, for the disease-free equilibrium, we have the Jacobian of the model 1, that is the model equation. A disease-free equilibrium is given by this, where G1 is equal to this, and G2, G3 are also defined. The eigenvalues of the Jacobian can be determined from the matrix equation, where I7 is the identity matrix, and the Rm is greater than 1, as it has been established for us to have a disease-free equilibrium. So this leads to the polynomial characteristics equation that we have in this place using this equation that is defined here. So we have this characteristics polynomial. So the B1 up to, the B0 up to B4, they are already defined as seen in this place. So from the equation 9, we see that the first two eigenvalues are this and this. Reason being that if we multiply this and this equal to 0, it means that either this is equal to 0 or this is equal to 0. And if we set each of these to be equal to 0, then we can compute this particular value. And each of them are both negative if Rm is greater than 1. Otherwise, the vector population will become extinct. Hence, the local stability of the disease-free equilibrium can be determined from the 5th degree component of the equation of equation 9, which is what we have here. So this effect, all the coefficients bi from I1 to 4 of the 5th degree polynomial equation of equation 9 are greater than 0 when RC is less than 1. So now, therefore, from the Descartes rule of sign, there's no sign change in the sequence of coefficients, and so the polynomial cannot have a positive rule. So since the polynomial does not have a positive rule, that means they have negative rules. So that is when RC is less than 1, all eigenvalues of the Jacobian are negative. And with this, it is established that the disease-free equilibrium is locally asymptotically stable when RC is less than 1 and unstable when RC is greater than 1. Then that moves also the endemic equilibria and also backward bifurcation. So the dynamics of the model 1 with constant ITN efficacy and no temperature effect is studied in the presence of malaria. So the endemic equilibria given by this of the model are computed as follows, as presented in this place, where A5, A6 have their representations. Then we have the equation 10 and 11 as the forces of infection. So the endemic equilibria are are obtained as a function of these forces of infection. So substituting 11 into 10. So we have substituting 11 into 10 and simplifying leads to this equation, where we have C1, C0, R1 to be what is presented here. So now, condition for the existence of endemic equilibria and the possible number for endemic equilibria to the model 1 with constant ITN efficacy and no temperature effect are given in table 3 and theorem 3.1. But we need to look at, okay, under what conditions does this become? Other words, we have condition for the existence of endemic equilibria and the possible number of endemic equilibria to the model with constant ITN efficacy and no temperature effect are given in table 3 and table 1. But looking at this equation here, we know that for us to have the endemic equilibria, then we need to know the kind of root that this equation should have. We know that having lambda VH to be equal to 0 is just a trivial solution. So we look at the one in the brackets. So we know that for this to have the endemic equilibria, it must mean that the root of this equation are both positive, because if it is negative, then that does not make any sense. Reason being that this gamma VH itself is the force of infection that contains the state variables, and having star represents the fact that the endemic equilibrium of those state variables. So having it therefore to be negative, we imply that one of the state variable also is negative as the endemic equilibrium, and that does not make any sense. So now, we need to look at the value of R1 and RC that can therefore make this root, the root of this equation, therefore to be positive, and that is what this table here cater for. Sorry. Okay. All right. So now, okay. So what we need to look at first is one: if R1 and RC are both less than or equals to 1, what is going to happen? If R1 and RC are both less than, if they are both less than 1, if they are both less than or equals to 1, what is going to happen? What that implies is that C1 and C0 will either be zeros or positive. Remember, I said less than or equals to 1. RC also less than or equals to 1. So if they are both equal to 1, then that means we're going to have C1 and C0 to be equal to 0, and that's just going to render it to be a trivial solution. But if you have them to be less than 1, for instance, if this is less than 1, this is less than 1, both of them will be positive. And we know that if C1 and C0 are both positive, that will imply that the roots will be negatives. And if the root will be negative, that means at that point we have 0 endemic equilibrium because it does not exist. So now, but if you consider the condition of maybe having RC to be less than 1 and R1 to be less than 1, what that will imply therefore now will be this here will be positive, while this one here will be negative. That may not also do, but the one condition that we do will be for this to be negative and this to be positive. So if this is negative, what it implies is that the sum of roots is negative, and with that we can have a positive root. With that we can have a positive root, in that we know that the multiplication of those roots will give us positive value in this place, and the condition under that which can happen will be, looking at C1 and C0, will be when R1 is greater than 1 and also RC is less than 1. And with that, we may have either 0 endemic equilibria or we have 2 endemic equilibria. All right, so we have the model equation. We have when when the ITN efficacy are set to be constant, the model 1 can have the following. We have no endemic equilibria when RC and R1 are both less than or equals to 1. One endemic equilibria if this is the case. 0 or 2 possible endemic equilibria if RC is less than 1 and R1 is greater than 1, just as I have explained in the previous slides. So per se of the last theorem indicate that the model might have 2 endemic equilibria when the reproduction number is below 1. But let us not forget that we also mentioned that all right, so we also mentioned that the disease-free equilibrium is globally asymptotically stable. So now let me just move forward. So here we have the pictorial diagram representing the forward bifurcation and the backward bifurcation and the parameters regime under which that occur. We have forward bifurcation when the human death rate is greater than the disease-induced death rate, and then we have the backward bifurcation when the disease-induced death rate is greater than the human death. That is what this one is just explained. So we can see here that here we have four bifurcation. This is at the point where we have 1. But at this point here, this is where R is equals to 1, and we can see that the value of R here is a particular value around 0.7 or something. And that occur for infectious immune humans and also the infectious mosquitoes. All right, so we have, so now the talking about the backward bifurcation now, it's a dynamic process that is characterized by the coexistence of stable disease-free and stable endemic equilibrium when the cellular production number of the model is less than 1. So in that case, we need to calculate the reproduction number that is necessary for the disease elimination using the parameter regime that brought about the backward bifurcation. And we have the new reproduction number here based on the new control reproduction number based on the backward bifurcation in this place. So simulation result for the cases with constant and waning ITN efficacy and constant or low temperature effect. So in this question, in this section, the model equation will be simulated to assess the impact of decay in ITN efficacy and temperature on the dynamics of malaria. So in all cases, unless otherwise specified, the simulations are performed using the baseline parameter values presented in the previous table. So we have the forward versus backward bifurcation. I've explained this in the previous. So we have the model is simulated to illustrate the possibility of forward bifurcation, and I've shown this also in the previous slide. And then this is the control reproduction number based on the backward bifurcation computed. So we have that thus a backward bifurcation occur for 0.74, which is the value for the backward reproduction number for the backward bifurcation, and it is less than the control reproduction number, which is also less than 1. Why the disease-free equilibrium is globally stable now when RC is less than this. So now we have the impact of ITN coverage, ITN efficacy, and induced. So in this section, the author look at now the previous one we have just looked at. We consider constant values for the ITN efficacy and also some of the parameters that are temperature dependent. But here now we are looking at the impact of the ITN coverage, ITN efficacy, and also ITN induced mortality. In this place now, the assumption of constant parameters ITNs are relaxed. So following the theorem 2.1 and lemma in this particular paper, the algorithm for computing reproduction number for periodic non-autonomous system is given by what we have in this place. Reason being that this is a non-autonomous system, so the reproduction number is not calculated as the issuer way for the autonomous system. So the reproduction number is the spectral radius this. So we have all of that. So it should be noted that F and V are of the same form as those obtained earlier for the constant parameters and constant ITN. A closed form for expression for the reproduction number cannot be obtained due to the complexity of the model. So here, a numerical profile of the reproduction number as a function of important model parameters is determined, and the threshold values of these parameters for which the reproduction number is unity are identified. So the figure we are going to see below, which is figure 4, represents show contour plots of the control reproduction number of the model 1 for the case in which ITN efficacy is constant. And that's what we are seeing here. We have, this is the case when the ITN efficacy is constant. This is when the ITN is average, while this one is the case when we have the decaying ITN efficacy. And it is tested on the ITN efficacy, and then we also have the mortality rate. So now, what does this one mean? Each of the color we have here actually correspond to the reproduction number in this place. And this one enables us to know, and then on the x-axis, we have the ITN coverage. This enables us to know the level of coverage that is needed in order to bring the reproduction number to 1, because the reproduction number is a metric that is used to see how the disease can be eliminated within the population. And mere looking at the constant ITN efficacy, we see that to bring malaria to less than 1, we are going to need, this is here we have one. We are going to need about more than 80% of ITN. We are going to need more than 80% of ITN. And also, if you are to look at the average ITN efficacy to bring malaria to less than 1, we are going to also need close to 80% of coverage. And also for the decaying ITN efficacy to bring malaria to less than 1 also, we are going to need close to 80% ITN coverage, rather, not efficacy. We are going to need about 80% of ITN coverage. Now, this is contrary to the World Health reports. For instance, now we have the figure shows that if ITN coverage is maintained at the baseline value of the 43% reported by the World Health Organization, which is used that we have the baseline value for the coverage, which is the B0, it is taken at 43%. That's the baseline value. So if the coverage is kept at this value, then we are saying from those contour plots that malaria elimination is impossible if ITN efficacy is average or decays over time. Then the next thing we're also saying is that, however, if the initial efficacy, ITN efficacy, and the ITN-related killing of mosquito are held at their base level as given in the table 1, then the figure 4 indicates that for 3% ITN coverage is required to reduce RC below 1. And what is the value of the? I think that's about 0.8. So let's see at the. So we have. So in this place, the ITN efficacy is taken as 0.8. We'll see that if we trace this now to this place, so this is the point where we have this is the area where we have the R0 to be less than. This is the area rather where we have the R0 to be less than 1. And we see that if we trace this down for each of the for the constant ITN efficacy, we'll see that just like it was stated here, that it indicates that for 3% ITN coverage is required to reduce RC below 1 if ITN efficacy is constant over time. But for the other values, which is average ITN efficacy, decaying ITN efficacy, keeping it at 0.8, 43-degree coverage will not be able to bring the R0 to be less than 1. As you can see in this place, this one is now a decaying ITN efficacy. If you keep it at 0.8, let's say this area, and we trace this to where we have 0.43, which is around this area, we'll see that it is not keeping the R0 to be less than 1. So similar explanation also go for the mortality rate. Keeping the mortality rate low, very low, maybe as far as let's say 0.14. From here we can see that to bring it to less than 0.4, mortality rate to 0.4, and then then looking at the corresponding value of R0 to be less than 1, what level of coverage that is necessary to maintain the mortality rate to be 0.4, or to increase it to 0.26, or to make it 0.25. So we also see in this place the level of ITN that is necessary under the constant ITN efficacy, average ITN efficacy, and also the decaying ITN efficacy. So approximately 55% ITN coverage is required if ITN efficacy is coverage, as shown in the figure 4, why 72% ITN coverage is required if ITN efficacy declines over time. So we can see now that if ITN efficacy declines over time, we'll need more ITN coverage. In contrast to what is reported here, we need 72% ITN coverage if ITN efficacy declines over time. And that shows all the impact of the decline in the efficacy of ITN on the malaria transmission dynamics, or to bring it to bring the R naught to be less than 1. So these coverage percentages increase with reductions in the initial ITN efficacy or ITN-induced mortality rate of mosquito. In particular, if the efficacy of ITN drops below 50%, then containing malaria using only ITN, when ITN efficacy is average or decaying over time, is impossible, as we have seen from these two. When it is average, we need about 55%. When it is declining, we need about 72%. So dropping it below 50%, therefore, will not be able to contain malaria, as shown by these contour plots. So assessing the impact of ITN coverage, lifespan, and replacement time. So what we have just looked at is the impact of ITN coverage, ITN efficacy, and then ITN-induced mortality. So the next thing we want to look at here is assessing the impact of ITN coverage, lifespan, and then replacement time. So the figure we are seeing here, which is the figure 5, is showing us the contour plots of the control reproduction number of the model 1 with decaying ITN efficacy and periodic ITN replacement time as a function of ITN coverage, the lifespan of the ITN. So now what we're just explaining is that if the lifespan of the ITN is, let's say, 2, it is 4, it is 5, or it is 6, what's going to be the impact of it on the prevalence of malaria? And at what level of coverage will the reproduction number be brought to be less than 1? And what must be the lifespan of the ITN for us to achieve that? Let's say, for instance, if the ITN coverage is 0.4, so we can see, if you take this up here now, as 0.4, it is near impossible. It is impossible to bring the R naught to be less than 1 when the coverage is equal to 0.4. It is, even in fact, for all levels of lifespan of the ITN. So we have here now that as in 39 and 40, the results indicate that ITN with longer lifespan outperform those with shorter lifespans in malaria control. Now, how can we prove this? Let's say, for instance, now, if the lifespan of the net is, let's say, 5 years, and we bring it down to this place, we will see that at 5 years, we will only need about maybe 50-something plus coverage of ITN to bring the reproduction number to be less than 1. Just 53, maybe 50-something plus level of coverage to bring. But if we have the lifespan, let's say, to be 3 years, for instance, now what level of coverage will be able to bring the reproduction number to be less than 1? So if we are to trace this back now to this place, we will see that to bring it to less than 1, we will need about maybe 60-something plus or 70-something plus, maybe around this place. Maybe for 3 years, we need about 70-something plus to bring it to be less than 1. Unlike what we obtain for when R is equal to 5, which will bring it to be less than 1 with less ITN coverage. And that is what we are seeing in the contour, and that's what is being explained here. That, for example, if ITNs with a useful life of 3 years are replaced, sorry. So we have that for ITNs with lifespan of 3 years, approximately 74% ITN coverage is required to contain malaria, while ITNs with a lifespan of 5 years only require 54% ITN coverage to contain the malaria. So we can see what I've just been explained in the with the contour plot. And apart from that, what about the replacement time? If it is replaced every 2 years, every 3 years, every 4 years, every 5 years, what would be the impact of it on the reproduction number as a metric to measure the curtailing of the malaria transmission dynamics? And that is what And that is what this one is making us to realize that for better, for example, if ITNs with a useful life of 3 years are replaceable after 2 years, 58% ITN coverage is required for containing malaria, while if the ITNs are replaced after 4 years, 88%, which is additional 30% ITN coverage is required to contain the disease. So just to summarize, ITNs with longer usage durations that are replaced before their useful lifetime expires are recommended for malaria control. And here we have the assessing the impact of ITN coverage and also temperature on the on curtailing malaria spread or malaria transmission. So we have in this place that to assess the impact of ITN coverage and temperature on dynamics of malaria, a contour plot of the production number of the model 1 as a function of ITN coverage and temperature for the scenario with constant average and decayed ITN's efficacy is produced, as we can see in this place. So I don't know who is making this mark on this somebody is making mark on this something.
Who is HP? Let's know the people that are here.
All right, so let me just quickly explain this. So we have the contour plot of the control as a function of ITN coverage temperature for the case with 1, constant ITN efficacy, average ITN efficacy, and decaying ITN with periodic replacement time. The other parameters for plotting are given, so the parameters are given. So what is this one making us to realize? It's just making us to realize the fact that okay, there are given temperature and also necessary ITN coverage that brings the reproduction down to be less than 1. For instance, this one is just making us to realize the impact of temperature on the disease dynamic. Let's take, for instance, now at 21.5 degrees Celsius, for instance, 21.5 degrees Celsius, we'll see that we will only need about 0.3, like about 30% of ITN coverage to curtail malaria. Although this 0.5 is not always the case. Maybe in endemic areas like maybe Nigeria, where we have temperature ranging from something like maybe 24 degrees Celsius, 23 degrees Celsius, up to 35, 36, 40 degrees Celsius, as the case may be in the northern part. So, but one of the things that is being seen here is that the result obtained show that malaria transmission is optimized at temperature of 28 degrees Celsius if there is no ITN coverage, that is B not equal to 0, as we can see in this place. At 28 degrees Celsius at this point here. So we can see that there is the high note is very high, but above it, we are having a kind of reduction, and also below it, we're also having a kind of reduction in the value of the reproduction number, and then increasing the ITN coverage also help us to know the level of coverage that is required to curtail the spread of malaria, especially considering the decaying ITN efficacy. So then we have the impact of temperature and some related control parameters. So that's what this one here is just showing us. It's just showing us the maximum biting rate scaling factor, the impact of temperature of that. So I'm sorry, I'm just quickly rushing now because of our time. So we have the global sensitivity, and the global sensitivity is just showing us the parameters that have great influence on the prevalence of malaria, and that's what we are having here: total infectious humans, and each of these parameters, they have what they represent. So, like for instance, now in this place we have the upper mosquito biting rates. The upper mosquito biting rate, we can see that the upper mosquito biting rate has significant influence on the total infectious humans, and also the human recovery rate, and also the incubation period also. Each of these, they have significant influence on the total infectious human population. And that's what we are having. The results illustrated in this figure 9 is showing us that the human recovery rate, the maximum biting rate, the scaling factor of this, the ITN coverage, the initial ITN efficacy, the probability of an infectious human infection a specific mosquito, which are represented by this, and the mosquito carrying capacity, they have stronger influence on the infectious human population. But beyond that, we have also considered in this place, and they are found also will have strong impact, strong influence on the total infectious human population. So here we have the impact of the mean annual temperature and temperature fluctuation. Sorry, my time is already up. So I think I will just quickly move now to the discussion and conclusion. So the model exhibits a backup application, stable disease-free and a stable endemic state coexist when the population number of the model is less than 1. So we see that simulation of the model show that when ITN efficacy is constant, average or when disease is impossible if all parameters held at their base value. But if they are modified, then we're able to see the required ITN coverage that is able to curtail malaria spread, considering the decay of ITN. Furthermore, the analysis showed that malaria control is improved by replacing ITNs before their intended lifespan. The model with constant or average ITN efficacy underestimate disease burden and the required control effort. These results are consistent with the work in 39 and 40. Yeah, so the effect of epidemiological metrics such as the control population number and the human disease burden of the interaction between temperature and certain parameters of the model that are affected by the control measures are also examined. So let me just go to the limitation of the study. One of the key assumptions of the model is that all ITNs are replaced simultaneously. That may not always be the case in the real life situation. Only the effect of temperature is accounted for. We know that the dynamics of malaria can also be influenced by other environmental factors such as humidity and precipitation, which are not considered in the work. Also, the author did not consider asymptomatic individuals that are major carriers of the malaria parasite. They were not accounted for in this study. And also, the study is theoretical. It did not include any malaria data to feed the model as to validate the result of the different scenarios that were painted in the work. The inclusion of the recovered class and what is represented are also malariologically questionable, in that the author made use of the recovered class and also say that the time it will take a recovered class to become susceptible again is going to be a kind of 5 times 365 days, which is going to be 5 years, meaning for that period of time, the person is not maybe it's not being further infected by mosquito, which will not be the case because malaria does not give permanent immunity, and there's no infectious blocking immunity developed as a result of exposure to malaria. All right, so but the strength of the study is also in the study identifies important parameters that can be targeted for control purposes and shows that accounting for waning in ITN efficacy is important in understanding malaria transmission and in estimating the effort required to contain malaria. The study also showed that malaria is extremely sensitive to seasonal changes in temperature. Furthermore, the study also showed that transmission risk is optimal at temperature of 28 degrees Celsius. This is different from the work of Mordecai, which said that the malaria transmission risk is optimal at 25 degrees Celsius. Thus, understanding the interaction between malaria dynamics, temperature changes, and waning ITN efficacy is essential in assessing the impact of temperature variations on malaria risk and in designing improved malaria control mitigation strategies. So at this point, I'm going to stop. These are some of the references. So thank you for listening.
Yeah, thank you so much, Mr. Chikaya, for your presentation. So please, if you have questions, comments, observation to make, let's signify so that we can take number. So while others are waiting, raising their hands, Mr. Olasupo, go ahead with your questions.
Thank you so much, Center. Job well done. Yeah, I just want to call your attention to a few things that maybe in the course of you rushing down the work, you were not paying attention to the correct way of presenting them. For instance, there was a point you were trying to talk about critical minimum, critical maximum. I don't understand. I guess those points are critical points, which can either be minimum or maximum, or you are saying critical minimum. So one wants to know if there's any other type of minimum, maximum. So I think you should not start. And then at the point we were talking about initial condition problem, I know also maybe because we are rushing, we'll be talking about initial value problem. Now, the interpretation of the contour plots, if you wish, if you want to go back to the contour plots. Show the contour plots. You will notice that in the course of your interpretation, the values that you were, in fact, I would love to go to use the second one so that, because that one is a bit, the second contour plot. Okay, yeah, we'll use that for instance. You will notice that the interpretation you were giving, if you go to the next page, now, go to the next page of that. I want to just point your attention to something there. Okay, now, next page after that one. Okay, so now you will notice that when, for example, if I TN with a useful lifespan, something at the place, after 2 years, okay, there's a place where you were giving a hair. While if they are replaced after 4 years, it's approximately 88. And then, okay, can you go to the next one before you come back to the...
This one is another.
Okay, so go back to the contour plots now. You will notice that when you were talking about 3 years,
there's another one here before the contour plots.
Is the contour plots that?
No, as in there's the explanation before the contour plot, which is still talking about the contour plot.
Okay.
There's the one after the contour plot.
There's a value that actually
so I want to be sure the one you are talking of. That's why I'm showing you this one too. Maybe it is this one you are
Hey, that's one.
That's what I want to show you.
It said for ITM with a lifespan of 3 years, you realize that the value you quoted was not was around 50 something. And that will be because of the way you are interpreting that contour plots. If you go back to the contour plots now.
Okay.
So now, like you said, if you want to put, you can put your cursor around that 3 years. Now, if you trace now, we believe that you have decided to choose 1 as maybe R not equals to 1 at the point equals to 1 as your critical point, as what is minimum, the minimum requirement, right? So if we trace that 3 down to that 1 at 3, yes, just trace it down to 1. So where we have 1 here. Trace it, let it get onto 1. Good. So that's what you should do. Now, if you look at that place where you have 1, you realize that the contour, is from up down, right?
It's from up down, like what?
Yes, do you mean by you see that everywhere you have 1, 1, 1, 1.
Yes.
So everywhere you have 1 does not mean when it's equal to 3, because it is only at the point where you trace from 3 down when you now bring it close down. So you see that we're having around 70 something, but you were talking 50. You were talking 50 because at the point we also took it to, you were taking it up that trajectory, and everywhere on that trajectory does not, you realize that everyone that trajectory measures variation in ITN lifespan as well as variation in ITN coverage. So that means that it is possible, for instance, if I have 1 at 100%, what's it called now? 100% coverage, I can as well, just come to that one and trace it, and trace it to the plots that are to the so, and then trace it down to ITN lifespan, so which will tell us the lifespan that is required. So at the same time, if I come to 0.8 for the ITN coverage, ITN coverage.
0.8.
Yes, 0.8 on the ITN coverage.
Yes.
So yes, and I take it up to that one as well.
Yes.
Again, I will need to trace it down to the left-hand side to
Yes.
know what the corresponding the requirement is each time.
Yes.
So what I'm saying is that this thing is not like it's not it varies along that trajectory.
Yeah.
So the values will be varying along that, both of them.
Yeah.
But I saw that you were giving 50 something percent.
Okay, actually, okay. I think I understand what you're saying. Actually, that was the way I was trying to explain it. So the 50% and 74% are actually for two different things. One, we have one for the ITN lifespan. We have the other for the ITN replacement time and the coverage required based on that. We have the coverage required based on the ITN lifespan and reducing the R to be less than 1. Then we also have the ITN replacement time, the coverage required to make R to be less than 1. So that's why you are having the two different. For instance, now, what we have here now, this one is talking about, as in this, the result indicate that ITN with longer lifespan, talking about the lifespan. We have the contour plot. This one here now is talking about replacement.
I think I understand what you are saying, but what I'm telling you is that
I understand what you are saying. I understand what you are saying now.
When you were interpreting your something, when you were doing the interpretation, you were giving values that were less than what the something originally should be. When you were talking about 3 years, sorry, can you go back? When you were talking about 3 years, what's it called? The 3 years lifespan, ITN lifespan. The coverage required that you were giving us was around 50. Whereas if you trace it here, it shouldn't be 50. You were saying 50, but so you see that it should not be 50. Yeah, it's 70. I'm not saying what you wrote, what you say. Okay, is what I'm talking about.
Oh, I think I remember what you were saying now. This is what we are talking about now. That was what when I was saying if it is less than 50%, that if it is less than 50% for the average, for the constant, and for the
it's okay. What I'm saying is what I've said.
It's okay.
That's what you said. What is not what you wrote, is what you said I'm talking about now. Based on what you were tracing it, and then you were saying that at 3 years lifespan, we are going to be having 50. We need 50. And I was really interested in seeing what you actually wrote, but I was happy that what you wrote was not that. So I'm just saying that let's the tracing actually. Okay, that's one. Then under the limitation, so you were saying that the person put R, but that is not correct because malaria does not confer permanent immunity. But I would say that the author has not said so. The author did not say that malaria conferred permanent immunity because that's why there's a movement from R back. So the author has not said so. So I don't know why you think that still supports what we're trying to say.
Okay, I think what I was trying to explain was that I said the inclusion of the recovered class and what it represented are myologically questionable.
Is the explanation concerning?
So, okay, yes, I was saying that. I says one, malaria does not confer permanent immunity, and then the author
didn't say so.
Yes, I'm just explaining. It was my explanation. It was during my explanation, and I mentioned that now the author cater for the rate of coming back to the susceptible class, and from the table he calculated that as 5 times 365 days, and that is equal to 5 years.
Yeah.
So it means that the person can remain in the recovered class for 5 years before going back to the susceptible class. And I was trying to say that that means the author is saying something like for that period of time, maybe there's a kind of infection blocking immunity, which is not the case. And I was trying to say that additionally, malaria does not even confer. I was trying to explain that malaria also does not even confer permanent immunity. I'm not saying that maybe the author claimed that. No, that is not what
so I am wondering that you actually had to allude to that because I was thinking there was no reason to mention that in the first place, malaria does not confer permanent immunity. Since you are talking about the limitation of the work, though I'm talking about what you said actually, that you have explained the fact that what it means to stay 5 years But now you now went further to say that, and much more, malaria does not confer permanent immunity. So I was wondering where you got that from. Like, because for me, it's not coming as a limitation because it has not been said. Rather, what is coming as a limitation is what you have said earlier, that is the author insinuated that somebody can stay in the recovered class for 5 years without getting infected. So having to now mention the other one, I was not seeing where that one was coming from. Yeah, so I understand that you want us to see that malaria does not confer permanent immunity. Yeah, it does not even confer any form of permanent immunity. So, well, I think it's not a limitation of that word. So what is limitation is what you have earlier mentioned, which is that the malaria does not even confer even the temporal immunity as insinuated, like immunity up to 5 years for somebody becomes. So I think that's what the limitation is, and not the other one. Thank you.
All right, thank you.
Bye.
Okay, thank you, Mr. Any other questions from your house?
Yes.
Okay, go ahead, Mr. Ugbojuri Akilo.
Okay. Yes, sir. Thank you very much, sir. Thank you, Mr. Sam. So my first question is on slide 5. I want to.
It was slide 5?
Slide 5, yes.
Okay.
So page 5, is it? This it's additionally accounting for both seasonal. So this line, additionally accounting for both seasonality and decay in ITN efficacy. I don't understand. What do you mean by accounting for seasonality in ITN efficacy? I don't understand that line.
Accounting for what? I'm not hearing you well, sir.
Accounting for seasonality in ITN efficacy. What does that mean?
No, not seasonality in ITN efficacy. Accounting for both seasonality and decay in ITN efficacy leads to complex malaria patterns, not seasonality in ITN efficacy.
Okay, because you say both seasonality and decay. That's how I'm understanding it too. But I think you've explained it now. But so maybe it's the way the thing came. So I was trying to understand what does it mean to account for seasonality in ITN. It's all right, sir. Thank you.
So
okay.
So what is I have that question as a follow-up question based on this statement. What is seasonality attached to?
Okay, the seasonality here is it's not on its own. It's not on its own. Yeah, I think that should be okay. I think I understand what Mr. Shaw is make reference to now. Maybe seasonality in malaria cases or
so seasonality observed in malaria cases.
Okay. So my second question is on the flow chart. Okay, so I see that there's transition from R to S and also transition from I to S. What's the difference between the two according to the paper?
The transition from
R to S and then from I to S.
Okay, the I to S, this gamma H actually is talking about the human recovery rate.
Okay.
The human recovery rate.
For most people, recovery rate.
Human recovery rate.
Yes. The infectious human recovery rate. Now, this one is more. This one is more of like natural recovery, maybe after the infectious period. Why this one here, the sigma H, is talking about the treatment rate. Wow. That's not the way the author used it. Yeah, you can see it. You can see it here. This is it. Duration of human infection. This is it here. Duration of human infection. Yes, that is it, you know.
But it's the same thing they are put there now.
Miss, see, so sigma H is duration of human infection, gamma H is human infection. It seems there is something is fishy there.
So from here to here, and from here to yes, I think in the explanation, it made use of one of these as treatments.
Okay.
It made use of one of these as treatment. I think this one is the treatment.
I suppose that IH will be treatment.
Yes, it mentioned
because
this one here as treatment in the course of the explanation, because in the course of global sensitivity and doing some other things, was mentioning for the use of ITN and also increasing treatment also in the course of the explanation. So I think this one is for the treatment, while this one is for the natural recovery rate.
Okay. It's all right. Well, it's not your work, so maybe if it's the author that is presenting would have probed this further.
Mr. Shimbot, I am thinking that, don't you think that this is actually a good one because I've always asked that question.
Yeah.
Except we don't agree with the fact that there's infectious period for malaria. So if we agree there is infectious period for malaria, then the question will be that that infectious period,
How long can it
like how long is it, and where will somebody
after the person has
because
left
infectious period, one of our infectious period is natural recovery rate. So if you don't take care of natural recovery rates and take care of only recovery due to treatment, then you may not also have taken care of a very important biology of malaria, which talks about infectious period. So if there's something called infectious period, then there should be something called natural recovery rate. So because I noticed that these days we seem to have removed it, and we only say that we only account for by treatment alone.
So my argument is if this guy who calls sigma H natural recovery rate, and then gamma H, which is also recovery due to treatment, should also go to R. So it should be two arrows coming from I to R, not one going to R and then the other one going to S. So that's where I'm a bit
right.
So
but I'm also looking at it from the perspective of what we are saying. That somebody like who didn't treat. You know that sigma H also, before somebody moves out of that high H, sigma H, if you look at the value, was larger in the table.
Yes.
The sigma H value, if you look at the table, you realize that it's larger.
Yes.
285. So I guess that would also be making, pointing at the fact that somebody who didn't take treatment will stay longer in the infectious class. And maybe when they now stay longer in the infectious, I wouldn't know. You know, we have always talked about this possibility of disease, anti-disease immunity, disease immunity, which somebody gets after you have been, which normally should have been for the asymptomatic person. Okay. But since they are not catering for the asymptomatic guys here now, so it may be that this guy is using the idea of saying that somebody who recovers naturally may have that kind of anti-disease immunity or something. I don't know. Maybe
although the here contain people that can still transmit the disease.
As you can see,
this R.
as you can see, I think
That's why we have this arrows. They can see
Okay.
yeah.
to the susceptible.
Therefore, asymptomatic we are talking
Yeah.
about.
So I think it will be the asymptomatic guys. That is
Yeah, so more
here.
like asymptomatic.
Asymptomatic.
But then, if we are saying they're asymptomatic, so we are saying IH also, they also become asymptomatic.
So and I think it's beautiful actually to look at it like that.
Yes.
Because if somebody recovers naturally,
you become
say
asymptomatic.
that the person
And then
asymptomatic.
So I think that IH should come
It makes
to
sense.
should come to AH.
So I think it's a good model for us to probe, and maybe we can gain a lot of insight from it too.
Yeah. Because for me, I'm seeing that we have always asked the question we have always asked the question of that if somebody, for instance, is asymptomatic, what happens when we are not catering? We are only saying that the person it's only when you have more infectious bites, the person becomes symptomatic, but actually becomes symptomatic again, which is the only thing that moves the person away from that class. But like I've said, we normally have we should believe that after some time too, an asymptomatic person too, but like this model now is making us see that like after 5 years, the asymptomatic individual can become susceptible, and then it's only due to then the symptomatic can be treated and all of that. So though it's not catering for the movement from the RH back to IH, but I think this part looks nice. We can discuss further, like you have said, sir. I mean, maybe we can even discuss this thing, and let's see what we have around this place. But let me make a plea. Let us discuss after we have finished our work.
So we must incorporate it. We must look at it and incorporate it into our model.
Let us look at it, though.
Okay. So my next question is also slide 16, equation 5.
16, equation 5.
Yes. Okay, so this equation 5, I really want you to, if you can speak to it and try to explain what is happening here. What is epsilon beta?
Okay.
So sorry, sir. Aronki, I don't know if you are the one, but the thing is showing that you are the one.
She's the one, Abi.
Yes, as if she's right, because it shows Ronke.
Yeah, me too. I saw Ronke Dorcas.
Where we have this star.
She becomes a hacker.
Be
she has become.
Look at what you are doing, because this thing is distracting here. If you are the one, please watch it.
Is she
I was actually trying to enlarge my screen. So the thing.
Please, your screen is already affecting everybody's.
How come?
I don't know why it's marking, but I was actually trying to enlarge my screen.
You
are the hacker.
You have click on marker or something. Maybe
I don't know how to do it.
But now, so how come you are the hacker here?
Boys, it's okay, Sean.
We will ban you.
All right, so Mr. Mr. Sean, just like you asked, so this is just explaining the declination in the efficacy of the ITN. This E naught here is the initial efficacy, which is the protective initial efficacy. This one is the killing. This one here is the killing efficacy, where E naught is the efficacy of the bed net for the protection and the killing mosquitoes. So T is the varying time from time 0 to whatever period of time or whatever length of time. Yeah, this E naught is the initial
epsilon
E naught. I mean epsilon naught. Sorry.
Is it epsilon?
Epsilon naught.
Is it epsilon? By epsilon naught.
By epsilon naught. By epsilon naught here is the initial efficacy, all right, the ITN efficacy. So this T is our time T, which runs from 0 to whatever the duration of time may be, where this capital T represents the useful, it's just like the lifespan of the bed nets. So now this equation is derived by the author. So I don't know the way it was derived, but there are other functions that can also be used to do the same thing. So what this one is just saying here is, for instance, now at t equals to 0, as time t equals to 0, for instance, as time t equals to 0, we are going to have the whole of this to be equals to 0, and at that, the whole of this will be equals to 1, meaning that at t equals to 0, when the declaration has not started, we have our initial ITN efficacy. But as time increases, the t equals to 1, t equals to 2, and all of that, then we have the declination. So until when we have where t minus, where t, capital T minus small t equals to 1, where we have t minus t equals to 1. But at the time where we have t equals to t again, you know, this is modular arithmetic, that will be equals to 0, making the whole of this to be equal to 0. Then we are going to have another jump. So the something is going to be like, if you look at my screen, I don't know if you can see the pointer, the hand, it's going to look like, since it's a decreasing function, it's going to look like something that go like a Gaussian function, something like that. And then pick up again, because there we have t to be equals to, we have t to be equals to t. So it picks up again, going back to the initial efficacy, then it declines again. When we have t equals to t again, then it goes off again and all of that. So it's just showing us the dynamics of the bed nets. And one of the assumptions that have been made here is that all the ITNs are replaced all at the same time. And that is the reason why we have at that t equal to t, we have a jump up again before the further declination.
Okay.
And the same thing also occurs for, the same thing also is accounted for the clean efficacy of the bed net. But in this case, there's an assumption. The assumption is that at the end of the lifespan of the nets, in terms of the efficacy, it is assumed that as t equals to t, that then the chemical will have waned and all of that, because it is the chemical that kills the mosquito that land on the ITN, that the chemical might have waned, and then the ITN will be half productive as its original form. And that is why for this one here, as t equals to t, this will be equals to epsilon, by epsilon over 2. So it's just a way of capturing the dynamics. It's just a way of capturing the dynamics of the bed net based on what you have.
Okay.
What come with that. Okay.
Okay. So what's n? What is n?
The n is more of a shape parameter. It's more of shape parameter. It's just a shape parameter. The n is a shape parameter that takes value from maybe 1, 2, 3, 4, 5, 6. But for this author here now, images of n equals to 6.
Okay.
Images of n equals to 6, yes.
All right. So then my next question is, I saw you talking about or presenting on the mosquito-free equilibrium. I don't know what's the significance.
I'm not hearing you so well, sir.
Can you hear me?
Not so well, sir.
Hello, hello. Hello, hello. Hello, hello. Hello, hello.
All right, sir.
Hello, hello. Hello, hello. Okay, can you hear me now?
Yes, sir.
So you talked about the mosquito-free equilibrium from the study. I don't know what's the significance of that particular equilibrium, and then what's the talk about its stability and all that.
Okay, the mosquito-free equilibrium.
Yeah, what's the significance?
Okay, well, the author introduced it, and I think while I was just going through it, I was also asking myself the same question that, okay, why the introduction of this? And I think one of the things I felt, I'm coming. Yeah, I think one of the things I just saw is that
So, Mr. Sam.
Yes, sir.
Maybe because
and we also have human equilibrium.
So I think the author just wanted to some exercise.
Okay.
Then I think you also use
realistic,
it
biologically realistic. You understand?
Yes, sir.
It is not biologically realistic. So most of the people that have worked on similar models silent about it.
Okay.
So, and whenever you include an aquatic stage mosquito in your model, you will definitely have that disease-free equilibrium. Are we together?
Disease-free or mosquito-free, sir?
The mosquito-free.
Okay.
It's a kind of disease-free also.
Yes, sir.
Disease is free and mosquito is free.
Yes, sir.
So you will definitely have it, but you don't have to do any analysis around it because it is generally stated that it's not biologically realistic.
Okay.
So that is it.
All right.
Thank you, sir.
Thank you, sir.
Dr. Afisa,
Yes, sir.
We have human free equilibrium.
That was what I was thinking. And also let's do an exercise on that too. To find the equilibrium
when there is no human being.
And then
why we have that was that we have situation whereby aquatic stations are disconnected from other mosquitoes, from other compartments. That was what happened.
Okay, sir. So that's all from my end.
Okay, so is there another person who is raising hand?
Yes.
Dr. David.
Let's have you.
All right. So mine is just one question. So up to your parameter table, I want to understand what is the current capacity now. How was that what is the that value there? We have 10 raised to the power of 4. I think so.
10,000.
Yes. So what is the rationale behind that?
Okay. Well, one thing is, this is a theoretical study. It's not data driven in any way. One of the things I can say is that for data driven work, one may want to carefully choose this particular value based on the population. Considering the total population of mosquitoes. Because one thing you don't want to do is for the total number of mosquitoes to be greater than the current capacity. Are you getting it now? So sometimes one use to carefully select the carrying capacity. So in most cases, it's kind of either one assume it or one find the kind of definition around it. Although there are, I've seen papers where they talking about making the capacity, but that may be a bit tricky in that you won't be able to control what the kind of capacity to do, and also position the materials.
All right, thank you, sir.
Okay, Dr. David.
Okay. Thank you very much, Mr. Summer, Mr. Shikoya, for that beautiful presentation. Actually, I have some observations. I noticed you didn't use the standard mode of presentation for preparing your slides. Yes.
Okay, ma'am.
So now my question for you is that I'm actually wondering how it correlates with your work, because I know you're working with why the choice of this paper actually?
Why did I what?
Why the choice of this paper?
Why the choice of this paper?
Yes, I know you are looking at ACT, so are you considering including ITN? Because I know that the major strength of this work is ITN, the efficacy of ITN,
Okay.
blah, blah, blah. So why the choice of this paper? So how does it have any contribution to your work? Why did you go for this paper?
Yes, it has a lot to do with my work. Because I'm not only considering what's it called? ACT. I'm considering ACT and LLIN. So, and it's even one of my research questions. In fact, one of the current questions I'm working on is on ITN, not even ACT. While I have ACT, I'm working on the ACT and non-ACT. And I also have LLIN that I'm working on too. So it's actually related. And that's why I even took my time to really study this. And
okay, thank you very much. So what do you think are open problems from this work?
Open problems?
Yes.
Yeah, there are quite a number of them. One, the author did not account for maybe the use of temperature, and also explicitly accounting for the use of ACT and possibly non-ACT as these interact with the climate variables and their combined effects on the malaria prevalence. So the author did not actually consider that. And just like I said also, most authors have used the carrying capacity as a constant thing. So one may be interested in looking at what happens if the carrying capacity is not constant, but because in the real sense, it is not constant throughout the year. It varies. And then apart from that also, yeah, I think those are part of them.
Thank you very much. And to the parameter table and especially we are talking about the gamma, the H and the rho H, going back to the susceptible class. I'm looking at the value. One is 60, one is 285. So are you saying that an individual will have to spend like 285 days before moving to the cover class? That's about like, is it not 6 months?
Yeah,
Because I know that for the ACT to clear the gamma cells from the bloodstream, it takes about 28 days. So I'm just concerned about that area.
Yeah. Actually, for the infectious period, I think one of the work done in 9.5 months. Yes, we have even I think I've even read the paper that the number of days for the infectious period is about 297 days. So it varies depending on maybe different experiment carried. But it is not in any way maybe wrong. And you also see that even the value is not fixed. We have range of values for that duration of normal infection. So that was I was trying to also give a typical example of. We have the case of 9.5 months. In fact, I think what's his name? Chitney's mentioned, if not 3 months to 50 years, something like that. 3 months to 50 years, Chitney's. So it actually varies. So making use of I don't think is something wrong or by the author. I think the author is still correct based on what he's trying to explain.
Okay, thank you very much.
You're welcome.
So David, well, I think that one may not interpret it also as saying somebody stays maybe being sick or
No.
You know that the I class as specified there is just infectious class. Like, so that would mean that the person will still be in that
is still carrying the gametocytes.
Yeah.
Still carrying the gametocytes for that long period of time.
I think is the transmission that determines that determines how long. So because the infection is the person may not have the disease but may have the infection. Because it's about transmission dynamics which depends on infection and not necessarily on disease. Maybe the author may be looking at it from that perspective that may take that long. But then I think it will become problematic, like you are pointing out, if somebody looks at it as symptomatic infection. Somebody wants to ask the question, how possible can you be symptomatic infectious for that long? So I think so maybe our presenter we want to help us read that portion so that it will help us understand it better.
So I think that one takes care of the question.
It takes care
of the question.
But he's saying that you should maybe our presenter will show light on it. Assuming you being a symptomatic.
In fact, I think I should critically say here that some of these things that we are saying here, the author did not explicitly explain them.
So you took your time, you spent time on it, you went to dig
to know what is not in the authors did not express.
We're able to say it out.
Through the mind of the author that has not been revealed on the paper.
I'm not really serious. God forgive me.
I think, are you satisfied?
Yeah, those are my concerns.
Okay, so thank you. So, Mr. Sam, so why did you have challenge with table and figure referencing?
Was actually say that it was the last running because I made some editing. So the last running I didn't even check if those things were affected. I think it was more of just putting the label to figures, naming those equations. So when I ran it, I just opened the PDF. So I didn't even go through to see all the question. In fact, when I was seeing, I was even surprised.
But if it is about the last one, it should not affect the previous one.
That was what I experienced, sir. But that was what.
No problem. So next time you take care of that kind of thing.
Yes, sir. Yes. Sir.
Okay, because when you are referring to figures and equations, only you are aware of the equation and the table you are referring to. So, and also lastly, is it sufficient to achieve malaria containment by just reducing the production number below 1?
But by just
reducing the because I heard you emphasizing on reducing the reproduction number below 1 for us to be able to achieve that malaria elimination or what have you.
Okay. Yes.
Is it sufficient to just reduce it, say 0.9?
Okay. Yeah, we may not really say it's sufficient.
Why?
Reason being that even from what we saw in the study, we have the issue of the backward bifurcation of which the reproduction number was calculated to be 0.74.
So that's where I'm going to. You will see that there is a critical point. They determine for reproduction number, but you didn't tell us the quantity of that value.
The quantity of the value.
Yes, if you are able to quantify that value, you'll be able to know how much we need to reduce reproduction number. Because you were talking about ITN coverage and replacement of something. How long how soon are people to get a replace the ITN usage, right? So you can't just say it's sufficient by looking at maybe 30% coverage. But if you are able to know that critical value, it will give us a critical bound where we must not go beyond, such that the elimination of malaria will still be possible.
So you decided about that, and it is good one take care of that kind of thing. So those are my comments. So others have been addressed by others. So thank you so much for your presentation. We appreciate everyone for joining this talk.
Ronke's hand has been up since. So,
Dr. Afisa,
Yeah.
I was just thinking about something again, sir.
Okay.
You know, the condition under which we have, I'm just thinking out loud, sir. So the condition under which we have the backward bifurcation, you know, we have the parameter regime, and we have the fact that the regime, we have that it was experienced, or it was observed when the disease-induced death rate is greater than the natural human death rate. So now, if the case is the fact that natural human death rate is greater than the disease-induced death rate, so do we still look at that critical value?
You know, those simulations were just illustration to achieve those situations, right?
Yes, sir.
So, but when you look at that mathematical expression, if you plot in all those parameter values, so you will see that you are going to get a particular value. So whatever value you get there, you will agree with me that, okay, if you look at a backward bifurcation plot, can you go there?
Yes, sir.
Okay, look at the backward bifurcation. If you trace that thing down,
but it's a certain.
That will give you RCDB. You can check.
Yes, sir. It was computed 0.74.
So that will mean that until you reduce the reproduction number below that value, the containment of malaria is still not, or elimination is still not possible.
Dr. Afisa,
yes, sir.
Is it outside of this interval? Is the 0.74 the critical value given? Is it without a recourse to the interval that is given here, the theta h?
Where
we are able to see a full application when the disease of this manifest is less than natural death rate.
Okay.
And we have passport application when the disease of this death rate is greater than the natural human death rate.
Okay. So they use that one to get to the scenario we have above here. All those gave us forward bifurcation, right? Yeah. But but whenever we have the backward bifurcation, you will see that they indicated RCDB. So under that scenario, where we have that simulation, you know, each of these scenarios corresponds to the dynamics. They have unique dynamics under that scenario, right? So if you take, for instance, the first one, where we have a backward bifurcation there, you will see that RCDB may be different from what we have in the second scenario. Then it's also different from what we have in the third scenario. And the value of delta H and mu H are not the same in those three situations. So we are now saying that as long as we have RCD, our RC be less than RCDB, the elimination of malaria is still possible. And when you put in the parameter value for that, the expression that we have, you know, we have mathematical expression. It will give you the RCDB value that this plot is indicating. So that's what I'm saying.
So, Dr. Afisa, I want to clear something here.
Okay.
Now, the data H are specified. I believe here that this is the backward bifurcation parameter.
They only settle for that. You can choose another parameter.
Okay.
Certificate.
Back to that. So actually, what me I'm saying is that in case I choose my, for instance, this parameter values in such a way that there is no, backward bifurcation is ruled out. Now, do I still need to consider in my so do I have to still look at the fact that my do we have to consider that critical value as the point? Exactly what I'm saying, because I guess the reason for giving us this range of values for delta H is so that the possibility of rolling out. So that's exactly what I was trying to point at.
Oh, that's good. So you will say that if they actually did that, there are many ways we can rule out the presence of backward bifurcation aside from doing this. So it will just mean that we want the bifurcation coefficient B to be coefficient A to be negative. That's the essence. So we look at the parameter that we can set to something that will make that apples. So that's the idea. So thank you. You said there somebody has questions or something. So Sister Aronke, do you still want to ask your question? Hello?
We can't hear you if you are talking. We can't hear you. We can't hear you online. Unmute your mic.
It's like she's not there.
Can you unmute yourself?
All right, sir. Thank you, sir. I was using my phone, so the battery is low. Like since I'm considering a particular project now, and I don't have access to real life data, And this particular work, according to the limitation now, we are having does not be validated with real life data. So I want to ask that in the result, how do they quantify those percentage decrease, percentage increase, and all that? How do they get it? So how do they get that result? So that's my question. In the coverage, you check your results, you see that there are some places that we have if there's a 80-something percentage increase in this, we have and so that's my question.
All right.
That's based on the baseline value.
Yeah, so the percentage increase, percentage decrease were actually calculated because we have we have instances where it was compared with all right, so we have instances, the percentage increase that you mentioned and all of that. Don't forget that the ITN coverage actually is in percentage. What is represented on the x-axis is actually percentage. And then we have baseline value for the ITN coverage. So relative to what is being discussed, so if there's going to be maybe additional increase in the ITN coverage, so with relative to what was called before, let's say for instance now, I think the base value used is 43%. So now, if from the contour plots, it is observed that we will need 72% to reduce the Gaussian number to be less than 1. So what you do now is that you look at 72 minus 43, we have about 29. So that means to achieve Gaussian less than 1, considering the scenario, we will need 29% increment in the ITN coverage relative to the base coverage. So that was how those ones were calculated. I was trying to find a particular, I don't know, maybe I didn't include it here or something. So like in the case of maybe temperature fluctuation and mean temperature, all of that, as I'm showing here, that won't even consider population of the infectious woman that will be affected, or maybe there's going to be an outbreak, or if something is going to reduce depending on the fluctuation of temperature and also the fluctuation from the mean temperature. So that also was discussed. So from here, what we are seeing here as maybe the contour plot is just like, it's more of like a 3D being projected on 2D plots in a way, because here we are seeing the temperature fluctuation, the mean temperature, and on this bar here, we are seeing the total population of the symptomatic infectious humans or individuals. So it is more like a 3D plot, but being projected on a 2D plot, so as for us to see that relationship. So it is from that those percentages we are talking about were actually computed from. So yeah.
Yeah, I think Mr. Sam as well, when you have when you are doing hypothetical study, you can also quantify hypothetically.
Hypothetically, yeah. Thank you.
Yes,
Thank
so
you.
it doesn't
Yeah.
have to be with data.
Yeah. Thank you.
Because some of these things, you say ITN from so percentage to so percentage, it's just from 0 to 1.
Exactly.
Which is 0% to 100%.
0%.
So it's just varying it across that. It's not like as if he's saying that in so place there was also percentage of ITN given that is leading to this. No, it's just a hypothetical study. I think it's okay.
Are we fine?
Yeah, I'm fine.
So thank you so much for your contributions.
You put it not clap.
So it has really been an engaging time. We enjoyed the presentation. We enjoyed the paper. We appreciate the author. Thank you all. So we'll see you next week.
Okay, we'll see. Yeah, we'll see you next week. Not at the